webinar of the winter semester, and today the webinar session will be opened by Denis Sipp. So let me first introduce him very quickly, and then I'll give him the stage. Denis Sipp is a director of research at ONERA and scientific officer at the Department of Aerodynamics, Aeroelasticity and Acoustics. He obtained his PhD in 1999 on the stability of vortex pairs. His primary interest has moved to flow control for instabilities encountered in aeronautic applications, such as black bodies, cavities, boundary layers, jets, vortices, and backward-facing stab flows. Both open loop and closed loop control strategies are considered with a special focus on linearized methods, adjoint techniques, model reduction, optimal control, and numerical simulation. So the talk of today is entitled Optimal Nonlinear Receptivity Analysis of a Flat Plate. It's with great pleasure that I introduced Denis Sipp. So Denis, I stop sharing my screen and I leave you the stage.
Okay, thank you very much, Francesco. So I share my screen. I don't know, do you see my screen?
Yeah.
Okay, I put it big. I don't know. Is this okay to everybody?
Yeah, we see the presentation mode.
Okay, very good. Thank you very much. So basically, this is a work that I've been doing in 2018 during my stay at Caltech with Tim Colonius and George Rigas. And it's about a transition in a flat plate boundary layer. And it's about a nonlinear transition. So this is the focus of this talk. And basically what I try to do here is to make something which is a little pedagogical and not too technical. So that's the focus of this presentation. So to introduce
Denis,
yes.
Sorry,
yes?
I interrupt you a second. Someone is telling me that the mic is not perfectly performing, so maybe you can just move it a little bit further with respect to, yeah, maybe it's
okay.
working.
Is it better here?
I don't know.
For you it's good, or I don't know.
For me it sounds okay.
Okay, because I can also switch from mic so that I go to the mic of my computer.
Let's give it a try.
Is it better like this?
Oh, that's much better.
It's much better. Okay.
Yeah.
So it's the okay.
Thank
Very
you.
good. Okay. So to introduce this talk here, I have presented a diagram of Reshotko in 2001, which shows the complexity of transition that may occur in a boundary layer, where depending on the disturbance level that is on the top here, and in the forthcoming presentation, it will be the parameter A, which is the strength of upstream noise that can be very weak to strong. And depending on this force, or on this amplitude A, you know that there can be various paths to transition. Regular transition, which goes more through eigenmode growth to transient growth to even bypass mechanisms. So basically the objective of this talk and the objective of this work was try to move towards an optimization framework where we tune A and try to find a little in an optimal way these various transition paths that are sketched here, A, B, C, D, E. Of course, you will see at the end that we have not managed to go over all these objectives, to this objective, but we have now a tool and a framework to do this in such a way. So, oops, sorry, I have to. Okay, so the outline of the talk is the following. So there are 4 parts. First, I will make a brief review of the various transition mechanisms, of the various amplification mechanisms that occur in a laminar-turbulent flat plate. So here we will talk about TS, bypass mechanisms, lift-up mechanisms, and so on. So it's just a brief review of this. And because I will afterwards, I will see how in this optimization framework we will obtain them again and how to combine them. Okay, and then in the second part, I will first go through what was classical up to now, which is a linear stability analysis with resolvent analysis. That means that we have a small amplitude forcing. You see, we have A, which is very small. So we have a disturbance level, which is weak. And in such a case, we can go through linear stability analysis. And then once we have achieved this, we move towards finite amplitude perturbations, where the forcing is now order 1. So it's order 1 amplitude. And as a first case, we will look at transition in a classical setting, which is K-type transition that was studied a lot in the 80s, 90s, and we'll just see how with the harmonic balance method we can study this kind of transition. And then in the last part here, which is 4, we will use this framework to optimize depending on A. So we fix A, and then we change A, and then we optimize transition, and to try to recover various paths of transition. So let me start first with my review. So the review of existing amplification mechanism. So we start here with well-known features, things which are related to the Blasius velocity profile. I just remind you here the Blasius velocity profile, which is given here. So this is the U profile, and this is distance to the wall. So this is a self-similar profile that is given here. And in the next forthcoming slides, I will represent everything in this diagram, because you see what I will consider is a flow field that is consisted of the Blasius profile, which is here, which is order 1. And then I will look at perturbations, which depend on time, which is here, U of YT. And these perturbations are characterized by a streamwise wave number, which is alpha, which is reported here, and a cross-stream, a spanwise, streamwise and spanwise wave number, which is beta, which will be here. So the Blasius profile, of course, is at alpha is equal to 0 and beta is equal to 0, because the Blasius profile does only depend on the wall normal direction, which is y, and does not depend neither on x and neither on z. So the Blasius profile, the base flow, is this big point here, which is here. And now we'll consider various perturbations of the Blasius profile. So this is basically a review of literature to show you all the mechanisms of amplification mechanisms that exist. So I will go a little quickly through them, but I would like still to recall them. So first of all, the most well-known and oldest instability of Blasius profile was Ts instability, where you know that Ts instability are instabilities of Blasius profile which are two-dimensional. That means that they are characterized by beta is equal to 0. So this is the strongest Ts instability. It's beta is equal to 0. And it has a streamwise wave number, which is alpha. So basically the following, I will represent this like this. So here, X is the streamwise direction, Z is the spanwise direction. And here I have represented iso phases of the perturbation. So basically this may be wall normal perturbation or streamwise perturbation. And this basically in time is convected downstream. Okay, and you can see that this represents to me a 2D Ts instability. And here I have just shown you a picture where you have a flat plate boundary layer. And here you see these small wiggles here are the TS waves. So this is just a picture to show you that this exists and so on. So this is a two-dimensional TS, very simple. Then once we have this in the 90s, 2000s, there has been, let's say, studies to show that these TS waves are secondary unstable. So these TS waves, once they are on top of TS of the Blasius profile, they can undergo instability. So this is a secondary instability, and there are actually two kinds of instabilities in this case. There is the fundamental instability, and there is what is called the subharmonic instability. So basically, to show you this, you see this is still my alpha beta plane. Here, this is Blasius. This is the TS wave. And if I consider fundamental secondary instability, that means that I will have a 3D instability, which has wave numbers alpha is equal to 0, alpha, 2 alpha, 3 alpha, where alpha is the initial wave number of the TS instability. So if it is a fundamental instability, the pattern of instability is like this. And what we will observe is basically that was TS. And if this TS instability becomes unstable, you see I have superposed here this wave plus a beta over 2 alpha wave. So it's this wave, for example. And what you can see is that I will have patterns that are aligned. You see, they are blue, yellow, and typically, if we let this evolve and go into transition, it will non-linearly evolve into something which is like this, where we have, you see, patterns that are aligned, blue, they are aligned like here. And this is something which is the non-linear evolution of that instability. So this is the primary instability, secondary instability, and the late stage of this instability is this picture that was taken from a PIV snapshots from KTH, Berlin in 99. These are streamwise velocities, which show you the late evolution of this secondary instability. If you have, if the instability is subharmonic, you see, for example, with respect to what was here blue was just on top of red. Subharmonic means that the instability that pops up, that is secondary and stable, is at alpha over 2. You see, instead of alpha, now the instability is at alpha over 2 and still periodic like this. And if you look at the pattern that is formed when this kind of stuff evolves, you have something that looks like this. So you can see that here we observe staggered patterns, like here, you see it's staggered, while here they were in line. So this is this was fundamental, why this is a staggered pattern. And this, in the late stage evolution, this will lead to H-type transition, where we'll see streaks which are in a staggered pattern. Okay, so this is from the viewpoint of Thomien-Schlichting instabilities. Then there is another mechanism that has been found in 1992, which is a mechanism which is fully nonlinear. That this fully nonlinear mechanism has been discovered by Schmidt in 1992. And in this case, you take two waves, you see, which are the two red waves here. So these are two oblique waves, one which goes in one direction on the left and the other that goes in the other direction. And if you superpose these two kind of stuff, you will observe a pattern which is like this. So plus, minus, plus, minus. These are two oblique waves that go in opposite direction, that go in opposite direction. And if you make them non-linearly involved, so this is not a linear mechanism, they will naturally transform into a streak which is here. You see, if you sum up these two wave numbers, you see this is beta over 2, alpha over 2, which is here, beta over 2 minus alpha over 2. You make the sum of this, you will have here beta, and here you will have 0. And so the end of this will be a vortex which is at beta 0. So basically, you plug this into Navier-Stokes, and then at the end, slowly but smoothly, you will see evolve not yet a streak, but a vortex at beta 0, which is like this. So this comes from nonlinear interactions, and this is what is called oblique wave interactions. And this is a very efficient way to trigger streamwise vortices. And then once you have streamwise vortices, there is a new mechanism which is completely linear again. This is called the lift-up mechanism, which will transform, you see, this is normal velocity, so these are streamwise vortices, into streamwise streaks. You see, this is whole normal velocity viewed from top, and this become streamwise streaks where you have Wx is streamwise velocities, where you have regions where the streamwise velocity is weak. This is where it is blue. So this is a streak. And regions where the streamwise velocity is high, and these are high speed regions. And so if you look at PIV, and if you initially insert two oblique, if you trigger oblique wave interaction, you have this, then it becomes streamwise vortices, and then at the end you have streamwise streaks, and this is exactly what is observed in this PIV snapshot in the boundary layer, where you have blue are the low speed regions, red are the high speed regions, and these are the streaks. So an efficient way of triggering streaks is to have oblique wave or two oblique waves, which become streamwise vortices, which then become streamwise streaks. And then once you have streamwise streaks, these also can undergo secondary instability. And these are the works which start in year 2000, something like this, which is exactly the same thing as secondary instability of Ts waves, but this time it's secondary instabilities of streaks. So you see here, we have the same pattern as before. You see here we have the Blasius, we have streak, and now we can have two things. Either it is fundamental, you see, that means that the secondary instability has the same wave number as the streak, or you have a secondary instability which has half of beta. You see here it's beta, here it's beta over 2. And depending on either you have fundamental or subharmonic, you will have either streaks that undergo a fundamental type instability where everything is aligned, like here, or where streaks are staggered. You see, you have here staggered patterns. This is subharmonic instability of streak, and this is symmetric, this is a fundamental instability of a streak. Then in terms of streaks, you see the initial streak was here symmetric with respect to z is equal to 0. You can also have a symmetric instability. This is the left row, or you can have an unsymmetric instability of the streak. And depending on symmetry, unsymmetric or fundamental superharmonic, you can have 4 types of instabilities, secondary instabilities of streaks. And basically this work has shown that the one that is most strongest basically is usually the one which is subharmonic unsymmetric. It's this kind of pattern that is most generic, especially when you have strong streaks. Okay, so these are secondary instability of streaks. Finally, I would like to mention a last mechanism that is at play in transition, in Blasius transition. This is a mechanism that has been discovered by Craig in 1975, where you have triadic resonances. And basically, if you have that kind of pattern, you see alpha, this is a Ts wave, 2 oblique waves, these 3 waves and the one that also exists because of the fact that the realness of each perturbation makes that you have automatically this and the one which is symmetric all the time. All of these waves will interact and will combine non-linearly and strengthen themselves, okay? And this again will promote a staggered pattern, which is like this. So basically, if you look at all of these pictures that we had here, it's all about staggered or unstaggered perturbations. And there are various phenomena that either promote a fundamental type instability, which is like here and here, or staggered pattern, which is like here and here. And these are things that we will see again afterwards, okay? So that was just a brief review of existing literature. And basically what we will do now is the first thing we'll do is go from a local framework of description of the instabilities to a global framework. And that means that in a local framework, up to now, we had that kind of perturbations, that we had a perturbation which depended on beta, which is the streamwise wave number, and in the streamwise direction there was a wave number which was alpha. And this is a local framework. And now we go to a global framework in which alpha will be replaced by omega. Omega is now a frequency, and you can see that the unknown now is W of x, y. X is still the streamwise direction. Y is still the whole normal direction. Beta is still the spanwise wave number, but now omega has replaced alpha. And there are everything that exists in the local framework can be translated into the global framework. And now what I will first do is look how linear instabilities, how they translate from local to global. So that's the setup that in a global framework that I will look at. So first of all, you see, I will consider the Navier-Stokes equations, which are here, and W will be my velocity pressure unknown. So W is Wx, Wy, Wz, and pressure. Okay, these are the nonlinear Navier-Stokes equations. And as you can see here, I have also considered F, a forcing, which is meant to represent upstream noise. It's the guy which will be responsible for triggering perturbations inside the boundary area. So it's the guy which will be responsible for the receptivity, okay? So F is a guy that represents upstream noise and that will enter into the system by this equation. So here we have Navier-Stokes equations that are forced by upstream noise, which is here, okay? N is just U dot grad U, L is the Stokes operator, and P is just a prolongation operator. As far as we, from now on, as far we contain boundary conditions, so Z is spanwise, X is streamwise, and what we'll consider in the forthcoming presentation is that we consider perturbations that are both periodic in time and in span. So in span, we will have a wave number beta, which is linked to the length of the spanwise direction, which is Lz. So beta is 2 pi over Lz. And in time, we are also periodic of period t, and this is a period, this is a frequency which is omega. And for the linear stability analysis, we will take both the forcing and the response, you see, as follows. So the forcing is a small amplitude forcing because we are in a linear setting. So we have a small amplitude forcing, which has a beta wave number and the omega frequency, and the structure, which is dependent on X and Y, X, Y, here, Z, and T, okay? And the response will be thought as an expansion, where W, basically it will be the base flow, or we will recover the Blasius velocity profile. And this will be the response to this forcing, which is here, okay? So basically here, we are not dealing with eigenmodes and global modes. because we will see that the boundary layer is fully stable, so that we have to introduce forcings to trigger perturbations, and we will be in a resolvent framework, okay, where we have an input-output relation. Input is F, and the output is our W, okay? So if we plug this inside the Navier-Stokes equations, at order one, here I go quickly, this is the steady Navier-Stokes equations with boundary conditions being the Blasius at inlets and at the top and 0 at the wall, okay? And if we solve this nonlinear equation, we recover a Blasius velocity profile. This is what I have shown here. You see on the right here, this is the streamwise Reynolds X. This is with my non-dimensionalization. This is the X direction, okay? And this is the displacement thickness that I have shown in form of a Reynolds delta 1. And as you can see, my solution that comes from free form, from Navier-Stokes discretization, the solution is in blue, and the Blasius exact solution is in red. And you can see that we exactly recover the Blasius evolution. On top of that, what I can also say here is that the Reynolds number based on displacement thickness, you see, is above 500, so that all of this region, which is here, is prone to Ts instabilities, because Ts instabilities, they start approximately at 500. So approximately for here on, I start having Ts instabilities. Also, in terms of friction velocity, you can see here, this is the solution and Blasius on the top, and it exactly follows the Blasius velocity profile. And in terms of transition, of course, this is laminar CF, and transition, of course, occurs if the friction velocity reaches the turbulent one that I have represented in green here. So basically what we will do in the next part is try to optimize so as to make the skin friction reach, the values of friction which are like turbulent values. Okay. So now if I go to the next order, so that was the base flow first. Now I go to next order, and here I have basically the resolvent, and this provides us with so this is a linear equation which provides us a linear input-output relation which goes from the forcing F towards the relation. So I have W of F. So for each F, I can have a W. This is a linear input-output relation, which involves the resolvent. And this resolvent is parameterized by beta and omega here. Okay, so these are parameters. And then what we basically do is that we optimize the forcing over all possible forcings. And here I normalize the forcing as being 1, and I look at the argmax, the maximum value of a given norm. And here the norm is the energy of the perturbation. So basically the optimal forcing is the forcing that triggers the strongest response in a linear framework. And the optimal response would just be the response associated to this optimal forcing. Here I just provide you a quick optimization result. So that has already been given in 2010 by Monocrusos in 2010. Okay. Here this is the frequency, the parameter frequency. This is beta, the wave number beta. And here you can see that we have various regions of strong receptivity. That means that if there is a forcing here, there is a strong response. And basically what is here, the point A, this is a streak. The point B, the point here, which is here, which is exactly, you see the peak, which is here. It's more here. This is pure Ts because it's beta 0 and at some omega. And there is another secondary peak, which is called non-modal Ts, which is a mechanism that has been discovered by Corbett in 2000. So it's a non-modal mechanism. So basically, I go quick here. So basically on the top here, if we look at the optimal forcing and optimal response, we have, this is optimal forcing is a streamwise vortex. And here the response is a streamwise, is a streak. That means streamwise perturbations of U prime. And if I look at this point B, I recover oblique waves. You see, these are the oblique waves, which are the optimal forcings and optimal response. Okay, so this is a linear framework where we nicely recover all the primary instabilities that I have shown you before. Of course, we don't recover here secondary instabilities because that would be instabilities of that guys, and these are guys that we look at now. So now we move from linear framework to a nonlinear framework. That means that now we consider finite amplitude perturbations, and we need to basically to consider finite amplitude perturbations to address the problem of transition, because the problem of transition involves the increase of CF. So at the beginning, CF was very small. You see, Blasius was here, and as long as you have very small amplitudes of the perturbations, your CF is still here. And if you consider finite amplitude perturbation, the CF can depart from here to reach turbulent values which are here. Okay, and that's the next step. So from now on, I take finite amplitude perturbations. This is a big A, which is order 1. And this is what we do here. So this is the same sketch as before, except that you see the forcing is not as simple as before. Here we have a forcing that is that has multiple harmonics. You see that a forcing is a sum of harmonics in beta and harmonics in omega. And now beta and omega is the fundamental frequency and the fundamental wave number, meaning that as everything is still periodic in Z and T, we will have beta wave number, 2 beta wave number, 3 beta wave number, 4 beta wave number, and also the same in omega. Omega, 2 omega, 3 omega, 4 omega, and all combinations of this. This is what is represented by this sum, which is here, and also the response also is also a sum over all harmonics, and this will trigger responses. Okay, so as before, we first know F, and then we look at the response W. So this is just an example, a small example to show you what is behind. So here, if we take a method where we truncate this sum, we just take 3 waves in beta and 3 waves in omega, which is here. And for example, this is the response. This is omega and beta. And so you can see that the response is looked for as a mean flow, which is the guy here, it's the red here. There is the green, this is a Ts wave because it's at omega 0. Then we have the yellow one, this is a streak. This is what is here is an oblique wave. And then there are symmetric ones, okay? So all of this form the response. And if I look at the forcing is similar, except that I will not allow a forcing at 0. This is just to restrict a little to forcing, not to force the system in a more subtle way. Okay, and if I introduce all of these equations, expansions into the nonlinear Navier-Stokes equations, I have a series of equations that govern the mean flow harmonic, this is W00, the 1, 0 harmonic, which is the streak, 0, 1, which is Ts, and so on. And as you can see, all of these equations are coupled nonlinear equations. You see, all of the W0 terms appear in all equations, and 1, 0 is there, 0, 1 is there. And you can see these are nonlinear coupled equations which are forced by these harmonics, okay? So then you can go a little too more general. I will not go into this, but this kind of system, we can solve it. We have, this was one of the major points to overcome is once F is given, we try to find the solution which is given by this system. Okay, and Here, this is a case which was documented by Rist and Pazel in 1995. And this is called K-type transition. And in K-type transition, you have an upstream forcing, which is a Ts wave and a streak. And what we, with our code, with this new code, we computed the response, which is here. You see, these are all the harmonics that we have computed and even more. And here we have represented all of these harmonics, the streamwise evolution of the energy of all of these harmonics. And what you can see here is that you see the Ts wave that was triggered here in the forcing, in an upstream forcing. This is the forcing region in gray. So it grows and grows because of the forcing, and then it saturates. And then we have also the streak, which is the blue one, which becomes stronger. And all of these harmonics which are here, they are non-linearly coupled, and they grow and grow, and this leads to transition. And this is called K-type transition. So here, what I just wanted to show you is that here we have a superposition of our method, which is the HBM method, which are the lines, and the symbols is the DNS from Rist. And you can see that we perfectly recover that kind of solution. So the HBM method is basically a way of putting a forcing, looking at the solution, but the strength is that we can also isolate unstable solutions. We can have limit cycles. We can have lots of solutions that you cannot see in DNS because they could be unstable. Okay, so the HBM framework is a general framework to find solutions that are both periodic here in Z and T. So it's a tool to understand the physics. Okay, so this I will let. This is just the solution that we recover. This is just a representation of the solution that we computed, with blue and red are the streaks, and blue and yellow are the streamwise vortices that are generated. This is typically K-type transition, where you have streaks that are aligned and not staggered as before. And this is a DNS from Sayadi et al. In 2013. And you can see that the first stage here, you see with a streak with these guys that you can see here. This is exactly a representative of this. So it's here we fully recover K-type transition. Okay, so now I move. Now that we have introduced the harmonic balance method and illustrated it on K-type transition, I move to the optimization of the forcing, because just here we took a prescribed forcing F. Now we will try to optimize it. Okay, so for this I just pose here what we optimize non-linearly. So basically, as before, I have my non-linear system. You see, this is my these are the Navier-Stokes equations which are forced. These are the boundary conditions, and this then generates a non-linear input-output relation, while in the resolvent framework, it was a linear input-output relation. Now it's a non-linear input-output relation. And once we have this, we form an optimization problem, which is this, which it is still an argmax, but this time the forcing has a prescribed amplitude, which is A, which is order 1, that I can tune, I can change. And as of the cost functional, I will not take the energy, but I will directly target transition. And targeting transition means that I try to target the drag, the mean drag over the flat plate. So for this, in J, you see this cost functional, I try to optimize the mean, the time averaged, and the spanwise averaged drag. And this is exactly related to transition, because if Cx or Cd increases, that means that I go towards transition. Okay, so this is what I have done. So we have optimized these guys, and this is now what I will show here. So this is basically, I will skip it because I see that the time runs. So here I just show you different optimization. On the left, it's the structure of the forcing. You see here, it's omega and beta, and this is the choice of the forcing harmonics. Okay, so all of these points represents a field that I have optimized. Okay, and all of these points here is a given harmonic. For example, this guy is exponential I omega t, exponential I 0z. So, okay, so all of these guys have a different structure, a spatio-temporal structure. Okay, and if I optimize that guy, so this is the response, and in color, it's the response. These are the harmonics that are strong. After optimization, these are also the harmonics that are strong in terms of optimization. And as you can see, if I optimize all of these guys, okay, I obtain this response, which is here. And you can see that this forcing is what is called a subharmonic forcing. It's exactly like the forcing that I showed you at the beginning, which are subharmonic. You see, the guys which were here, for example, alpha, beta over 2, you see that kind of things. These are subharmonic forcings. So we recover here naturally by optimization, we recover subharmonic forcing. And the response that we have is very strong at this guy. This is a streak, okay, which becomes very, very strong. And also, what you can see here is that the increase in drag, well, it's something like 1.53, and so you can see that this is the optimal. Now, if I remove harmonics, you see, for example, here I have let all of the guys being optimized. If I just take these two guys to be optimized, I obtain nearly the same increase in drag. See, before I had 1.53. Now I have 1.52. Okay, so obviously the subharmonic forcing is the guy which provides strongest transition features. Also, if I suppress the guy which is here and I just optimize these two guys, I have 10 times fewer. You see, here initially I had 1.52. Now I just have 0.1. Okay, and if I even go further, if I just optimize this one, this is oblique wave forcing. This is what was in the literature called oblique wave transition. This is even smaller, you see, with respect to this one, which was 0.1. This is oblique wave. And if I even go restrict more the forcing, if I just take streaks and nothing in omega, it's even much weaker, you see, what I can obtain. And if I just take TS waves on the right, it's even worse. Okay. And K-type forcing is this is just taking this harmonic and this harmonic. I have a very, very small increase of delta CD. So the potential for making transition, for triggering transition, of course, the best guy is the subharmonic instability like this. And in the 70s, 80s, people were a lot looking at K-type transition. K-type transition is not very powerful in triggering transition. What was even better first was oblique wave transition. So this is the scenario which was more in 92, 2000, okay. And then when they went to streaks, subharmonic instabilities like this, then that's the strongest potential for transition. Okay, so this is just to give you a little an overview of this different type of forcing that will recover nearly all the transition scenario that existed in the literature, depending on the restriction that we perform on the harmonics that we choose for the forcings. And now I would just like to show you some pictures of the guys that we have optimized. Okay, so here I just take some time to show you the optimals. So this is oblique wave forcing. Basically, it's transition which is linked to this guy or this guy. Okay, and as you can see here, if I take oblique wave forcing, what is strongest is basically the streak here. So this is basically what you see here. You see. The streak are the blue patterns here, okay? The blue patterns here, these are the streaks, okay? Low velocities. And the green stuff here, these are the streamwise vortices that go on top of these vortices, on top of the streaks. What we have then represented here, this is more the solution, and here we just look at some harmonics. If we look at the solution that just at harmonics beta omega and beta minus omega, we recover here the oblique waves, okay? Oblique wave forcing triggers oblique waves, okay? And then we can see here, if we look at the 2 beta component, we can see here in the solution that there's these oblique waves, they first generate streamwise vortices, which are the yellow and green ones. You see, yellow and green are the streamwise vortices. And just a little further away, we have the streamwise streaks. You see, blue and red are the low and high velocities in the streamwise component, okay? So here we have the full sequence where we have oblique waves that are generated by the forcing that become streamwise vortices by the oblique wave interaction, and then they become streamwise streaks by the lift-up mechanism. And finally, you can also see the subharmonic instability. You can see that you can see a staggered pattern, which is characteristic of varicose subharmonic streak instability. Okay, so here, when you optimize basically for a given amplitude, order 1 amplitude A, okay, you see that the optimization algorithm basically he takes the basic amplification mechanisms that exist, it combines them to amplify as much as possible the perturbation so that we increase the mean drag. Okay, so this is basically a full sequence that leads to transition at the end. I can also look at subharmonic forcing. So you see here it was oblique wave forcing. Subharmonic forcing is even stronger. So subharmonic forcing means that you trigger with the forcing both oblique waves, which are the blue and red, and also the Ts waves, which are the guys which are here. And again, here, thanks to the triadic H-type resonance mechanism of Craig that I mentioned at the beginning, this very strongly amplifies and triggers with also oblique wave interaction and lift-up mechanisms, again, the streaks, which then at the end also undergo a varicose subharmonic streak instability. So you have in sequence nearly all the different mechanisms that were discovered in the past in the literature, and then that are one after the other to try to amplify as much as possible the perturbation so that the skin friction increases as much as possible. Okay, just 2 last pictures. This is up to now, it was symmetric in Z, but the guy who is the strongest, you see the instability, the streak instability, which is the strongest, is the sinuous one. And if you go to unsymmetric in Z perturbations, you also recover that kind of perturbations, I think, which are the most ubiquitous that you can observe in transition in experiments. It's basically the strongest instability that is actually at hand. It's this guy. So if we take unsymmetric ones, these unsymmetric ones is really what goes as fast as possible to transition. Just to come back to what we were mentioning at the beginning, that's the skin friction as a function of the streamwise distance x, CF. This is laminar boundary line. This is the Blasius. And all of these lines are relative to different optimizations for different amplitudes. So if the amplitude is very small, you can see that, you see 9 to the 10 to the minus 5, you stay close to Blasius, okay? But as you increase the amplitude of the noise and the disturbance, you can see that the CF overshoots and reaches the skin friction of turbulent boundary layers. You see, this is the CF of turbulent boundary layers. And you can see that at the end of the plate, after the transition has gone through, we reach CF values which are close to turbulent, okay? And as you can also see, it's the unsymmetric patterns which are here that go towards transition, while everything that is symmetric remains close to Blasius. Also, a last picture here is that if we look at the profile, you see the whole normal profile of the mean profile. If we go from up, you see from upstream to downstream. So these are different profiles. Basically, what we can see, the more we go downstream, the more our profile goes from Blasius, which is here. This is Blasius, okay? This is upstream. And if we look at downstream profiles, we go towards profiles that exhibit the log layer region, which is here. So you see, this is in log. This is U plus U over U tau, etc. So here we are even more in the turbulent boundary layer. We'll recover mean profiles that are turbulent-like. That means that we have a log layer at the end of the plate, which is here. Okay, so this is basically a quick overview of all this optimization stuff, where we have various parameters, and basically what we can see in terms of conclusions is that the optimizations builds up on basically different elementary building blocks. It puts them in sequence to try to make the best of what it can to increase the drag, okay? And basically at the end of the plate, once turbulence is reached, we recover first features of turbulent boundary layers. Now, of course, this is the mean profile which is here, and this is something which is quite interesting, to go from linear transition towards the full sequence of nonlinear sequences that goes towards full turbulence. In terms of perspectives, of course, there is a lot to do, still a lot to do, because up to now, it was just incompressible Navier-Stokes equations, just a flat plate. Of course, if you have adverse and favorable pressure gradient, the picture is different. You can also have a sweep with cross-flow instabilities. This is 3D boundary layers. And one of the things that we are tackling at the moment are supersonic and hypersonic boundary layers, because there is a very nice applications in high-speed flows, because in high-speed flows at high Mach, you see in that vehicles, there is a low Reynolds number. And so there is a difficulty to make boundary layers transitions on that kind of vehicles. And we try to apply that kind of formalisms in a compressible framework to try to trigger transition in environments which are not favorable for transition. There are, because of the low Reynolds numbers, the high Mach numbers, it dampens a lot the instabilities. So we try to apply this framework to try to optimize the transition path, to optimize the transition, so that hypersonic vehicles can work fine in terms of boundary layer ingestion in the inlet, in the air inlet, so that it works well. So this is basically one of the applications of this, but there is much more to do. Of course, there are much more details in a JFM paper that is here, that has been published in 2021. This is just an overview of what is here, and I hope that I have made it a little clearer and given you a broader perspective about boundary layer transition and how all these results relate to past studies. Well, that's it, actually, Francesco.
Thank you very much, Denis, for this very interesting talk. And I would say we can open the floor to discussion. So whoever wants to ask a question, just feel free to unmute your mic and ask the question. Hi, Hendrik. Go ahead.
Hello. May I ask a question?
Yeah, sure.
Of course.
Thank you very much for the excellent presentation. I enjoyed it. I have a question regarding the remark that you made regarding the harmonic balance method to find unstable solutions and limit cycles. Did I understand it correctly that essentially the method is kind of a spectral method in Z and in time, and then you find nonlinear solutions, right?
Exactly, by Newton method.
Ah, okay. Mm-hmm.
So but it's not by time stepping. It's not by time stepping. It's a Newton method that targets exact solutions.
Okay, I understand. And would it be possible to give up the periodicity in Z?
Yeah, of course. The first HBM, of course, was devised just in time, and the initial HBM that exists, you see, Hall et al. 2002. It's just in time. But of course, in this code, if you take just 1 0 harmonic in Z, it's just in time. So you can have also just time periodic solutions, which are 2-dimensional, no problem. So of course, there is the initial HBM, the most easiest one is just in time.
I see. Okay, yeah, but. Okay, I was more like asking maybe if the period in Z becomes very large.
Yes.
Then you have to probably have to take care of many harmonics in Z.
Yeah.
And then the load, the numerical load becomes too large, maybe.
Yeah. Well, first of all, the fact that we have to cope with all of the harmonics makes it an expensive method. First of all, of course, the more harmonics you have in Z and T, the more difficult it will be. That's for sure. Another restriction here is that at the moment, I just have one fundamental frequency. That means that I have beta, 2 beta, 3 beta. But of course, there are extensions if you have incommensurable frequencies. You see, if you have 1 and 1.13, you have to take that into account exactly. Okay. So, but what I would like to say, HBM is not what is developed today. Still, there is another method which is called TSM, which is easier to do. Okay, and which is more straightforward, and where you can do a little all what is here in the time domain, okay? But, and it's a little easier. There are lots of people doing that in turbomachinery, in all that kinds of flow where there is periodicity and things like this. So I would rather say that, you see, this appeared in the aeronautical industry in 2002 for turbomachinery, and they have worked a lot since then. I have just taken this method, implemented it to look at transition stuff, which has not been done yet. That's a little, and what I have added is basically periodicity in Z, because transition is a matter of periodicity in time and in Z, because it's a spatial temporal complex problem, basically. But HBM existed a long way. There are lots of references. And but I think it's something also which is linked to lots of studies on restricted nonlinear models, on also the model of Galler, which is mean field. I don't know. I don't really. There are lots of things that relate to this, and this is the generalization of all of this of these frameworks.
Thank you very much. Thanks.
Any other question? Just once again, just feel free to open your mic, or if you cannot use your mic, you can just write in the chat. I can report a question. Then I would like to ask a question myself, and then maybe there will be someone else who just joined the discussion. So a question that's very practical, but that's at a certain point it's going to be somehow interesting to discuss. I think you showed several different mechanisms to trigger transition to turbulence, and you discussed them as efficient and non-efficient based on how, or powerful or unpowerful based on how they actually manage to trigger the transition and how fast they manage to kind of build up friction at the wall. And I ask myself, is this a robust description with respect to a rough plate? Like usually if you target like applications, yeah, we can talk about flat plates, but sometimes roughness is an essential parameter to characterize the transition that can induce it.
Yeah, so concerning this, what I can say is that up to now, if I come back to my equations, is that the forcing which is here are volumetric forcings. Okay, so it's more linked to forcings which are in the free stream and things like this. But exactly the same formalism could also be given for F representing a roughness at the wall. Okay, so it can be F could be I don't know a wall norm, a wall height, you see, of the roughness, and this same framework could also be applied to transition triggered by roughness issues. Okay, so here again, I think I'm not sure that we will recover exactly the same transition sequences, because if you are at the wall, if you just have roughnesses, first of all, you don't have a frequency mechanism, because up to now I had oblique waves with that combine beta and omega. If you just have references which are steady, the question is, where is the time stepping in? Because if you just have streaks, you can go towards transition. It's a little what I showed you here. You see, if you have streaks, so and no time, you increase delta CD, but much more weak as if you have time. You see, if you force also time inside the upstream forcing. So that's also something interesting, is to move from volumetric momentum forcing towards wall forcing only, and in this case also restricting, I would say, to steady forcing, because roughnesses are more like steady forcings. Then it's a different story. So if you just have roughnesses without excitation in time, you could have a delta CD which is much weaker and more difficulty finally to transition towards turbulence. But basically what is shown here is a quite versatile framework to try to look at input-output dynamics. Input could be things which are in the free stream, perturbations, but it can also be wall roughnesses that you could optimize and look at how to place the roughnesses in an optimal way so as to trigger transition. Okay, so this is of course something that can be done here. And is it robust? This I can't say, because of course forcing inside the domain in a volumetric in a volumic way is not at all the same as forcing at the wall, because if you force at the wall, it's not obvious that you manage to trigger perturbations in the outer part of the boundary layer and so on. So there is again another story that has to be studied if we want by this framework, but it's possible, but still has to be done. And I think there is still a big path between, this is a very fundamental study, which is conceptual, and going towards applications where you restrict the input to to be close to the wall, or to restrict the input can also be actuators that have restrictions. So there is a thing that steps in where you have to model what is P. You see the P, which is here. Up to the moment is just restriction or prolongation, but in P there can be much more. There can be an actuator, there can be, I would say, a roughness, but all of this has to be modeled. And of course, this is also a good follow-up, is to particularize F hat to something physical, and to look at finally the transfer function from F hat to the flow, and this will be taken into account by this P.
Okay. So basically, what you propose to take into account roughness would be to basically model it as a body force, or kind of?
Well, I don't say how it should be. I think any modeling can be. Of course, I don't like to, you see, just for example, if roughnesses as a first model can be modeled by what is called transpiration. So it's wall normal blowing and suction. This is very easy to do. So in P, it's very easy. This is something which is really linked to the gradient of the mean flow zero. You see, it's U dot grad. So this is very easy to do, but this is the first model. And if I discuss to colleagues who make roughness, they say this is a very poor representation of roughness, especially if you go towards amplitude 1 roughness. And as the whole point here is to consider order 1 amplitudes of perturbation. So we have also to consider here roughnesses that are not extremely small. So at some point, this modeling, as with transpiration, may be not sufficient to represent physically a roughness.
Okay. And this leads also the considerations you did. They somehow lead to my second question. It's the other way around, actually. So as you talked about jets and actuators for flow control, basically we could imagine also to go the other way around, that kill the optimal disturbance to relaminarize rather than transition into turbulence, such to eventually gain in terms of drag.
Yeah, of course. The question is, once you have said this, what would be the good objective functional? And in this case, well, it's all about optimization. You can still, for example, you could also imagine, you can think about it, a min-max problem, where basically you optimize a control device, for example, somewhere, so that an objective is as low as possible, while there is another guy, let's say nature or God, which optimizes in the other way around. And he will try to optimize the upstream perturbations so as to have the strongest output, okay? And so this could be another thing that could be done afterwards. So here, for example, in this case, F hat could be more, that's basically its nature that optimizes to make it as big as possible. And me as a controller, I will try to go in the other way around to try, and tune somewhere control parameters to make it as small as possible. And so in this case, you are in a framework of min-max optimization, where you try to optimize the parameters of a controller. And on the other side, in sequence, you can make one, then the other, then me, then the nature, then me. And at the end, you find an optimum where you hope that your cost function, which is perturbations, which is turbulence, that is as small as possible, okay? Whatever the perturbations that the nature will throw in by optimization also. So what is here, of course, we have just optimized in one direction, but you can also make a min-max problem and try to trigger questions like what you say. That means that I have a system and I want to relaminarize, and for this I have to tune parameters while there is somebody who plays against me. You see, all of this is possible, but has to be, of course, implemented and things like this. But again, you see, this optimization framework is extremely versatile. So you can basically apply it a little to everything. What is nice is that it's compact and it represents nonlinear features, while usually you just have linear. You just have linear. You see, resolvents are linear, so you cannot cope with objectives which say it's turbulent or not. While here, we can say, is the state turbulent or is the state not turbulent? And I think this is a major step with respect to linear frameworks, resolvent frameworks, where you just look at the first stages of transition, but which are not, to me, representative of full transition. You see, it's not because you have an unstable system, which is, for example, Ts unstable. If you just trigger Ts instability, you will never reach transition, turbulence, because Ts waves will saturate very quickly, and at some point you need something else. You need secondary instabilities, you need a whole path towards transition and the nonlinear representation of the solution.
Okay, very, very clear, very clear. Okay, let's see if there is someone else who wants to ask a question. So just feel free once again to unmute your mic and pose your question. Or you can even write in the chat once again.
Hi. Hello, can you hear me?
Yeah, go ahead, Pierre.
So I have perhaps a simple question. Why is the response not having the same number of time harmonics, or why it is having the same number of time harmonics?
Okay. So first of all, what I can decide on is, in terms of forcing harmonics, I can decide whatever I want because it's how I imagine the forcing is. Okay, so I can just say I want just this forcing, okay, but the response will develop nonlinearities, nonlinear interactions, and you have to go as far up to the point where you have blue points here. That means that you have zero amplitude, so that you don't constrain the solution. You see, you should not. You have to represent the solution so that it can develop in the harmonics. Okay, so you need to go very far in beta, very far in omega, but still, as it becomes computationally challenging, you want to restrict it or it becomes too expensive. And so basically, first of all, what is and that was also in RIST and in all the studies, in beta, the harmonics, the nonlinear interactions go much further in beta than they go in omega. This is, it's to me an observation, and the nonlinearity is much stronger in beta than in omega. This is to me an observation. And for example, if you do DNS simulations, for example, like this, in RIST, there are much more harmonics also in time, and you can see that very, very quickly, they drop very quickly. So in terms of amplitudes. So at the end, what you have to cope with is more the number of harmonics in beta. So for example, if you look at features like streaks and features like this, they develop very strongly in beta. You see, the more you go on the right, the more it becomes wavy in beta. Okay, so you have to take a lot of harmonics in beta. While finally in time, in terms of, you don't go very high in time. That means that this thing which is here is not very high frequency, actually. And I think one of the basic, what explains this is that if you look at the basic mechanism that I showed you at the beginning, which are the secondary instabilities, for example, of the streaks. Secondary instabilities, if you have this beta, so these are just the streaks which are there, they develop in beta, actually. Okay, they are strong in beta, and it's where there is the strongest nonlinearity. While the secondary instability in Ts, which is more what is here, actually they fall very quickly here. So they do not go very high in alpha nor in omega. Actually, that's actually, to me, I would say more an observation, but it goes with the picture that we have. You see, if you look at the picture on the right, they are extremely wavy in beta. That means a high number of harmonics in beta, but in time, in frequency, and even in alpha, if you look at the structures in alpha, they are not that, they do not go that in small perturbations. But still at the end, if you increase amplitude and if you go towards the end here, let's say if I show you these pictures here, at the end, at some point, you see there is a large number of wave numbers in beta, maybe a little smaller numbers in alpha or in omega, but at some point it explodes everywhere. Okay, so definitely the methodology which is here is not as good as DNS in terms of representation, and because I would need a lot of harmonics in beta and omega. Okay, but it's a very good way of identifying limit cycles, early stage transitions. You see, it's the starting of transition, the first nonlinear interactions that then go towards turbulence and skin frictions, which are close to turbulence. But I think the more I go on the right, at some point, I will need a lot of harmonics in beta and omega. And at some point, the methodology which is here will become inefficient. And at some point, it will not be possible, I think. Yeah, for sure, for sure.
Thank you.
Okay. So thanks for the question. Is there someone else who would like to ask a question? Okay, so that's, I remind you that you can write in the chat just in case you don't have access to a mic. Okay, so this does not seem to be the case. So thanks again, Denis, for the presentation, and it was a great start for the webinar of this year, of this semester. And I remind all of you that you could find that we have a webinar basically every week, and you can find the talk of today on the YouTube channel of LMFL. So don't hesitate to visit the YouTube channel. I will post it within a week at most. So thanks once again, Denis, for the talk of today. It was so interesting and it opened a lot of discussion. So that's good. Thank you.
Thank you very much. Thank you, Francesco, for the invitation.
Yeah,
it's very nice.
Good evening.
Thank you and bye-bye.
Bye-bye.